Hi. I'm glad that we are many people and not just the three people that were at the beginning. That was a bit sad. Okay, so today I want to talk about an extension of the concept of categorical magnitude, still like on progress, I would say, in the direction of information theory. Okay, so maybe these words don't mean anything to you, and I'm gonna start explaining what's magnitude. Piero, could you tell me maybe 5 minutes before we're done? So what's magnitude, and then and we'll move from that and how entropy enters the story. Okay. So again, pretty much as Paolo, I won't define a category, but in fact, the category is given by a set of objects, which we are going to suppose finite. So it's a finite set of objects. And then between any two objects, you will also have a set of morphisms, or like you can imagine like arrows, or like this sort of processes that go from one object to another. And what makes it a category is like these processes can be composed. Okay, so there is a composition law. So we start with a finite category, and then you can define this set of function. So the zeta function will be a function that for every pair of objects is going to count how many morphisms there are. Okay, so we're supposing with finite that this is also finite. So this is a function, and you can define also a weighting and a co-weighting. So weighting, so you can imagine that this is a matrix, and a weighting is just like a column vector. So the matrix times the column vector gives you a vector of ones. And a co-weighting is like a weighting for the transpose. Okay, but you can also define it this way without writing a square matrix. And then Leinster proved that when a category A has a weighting and a co-weighting, then in fact the total weight, if you want, is the same. And he called this quantity the magnitude of the category, okay? And it's written like this, like an Euler characteristic. In fact, it was called at the beginning the Euler characteristic of the category. And well, he said, in fact, that in this case, A has magnitude, okay? So this is Leinster terminology. But we'll see if we can do better in a second. So the magnitude of posets, in fact, not any categories, but posets, was already introduced by Rota in the 60s. Okay, so he also used the term Euler characteristic. And in fact, in that case, you can take the zeta function and invert it. So there's an inverse matrix mu. Okay, and this mu has a combinatorial interpretation. That's why Rota was interested in it. In fact, this Möbius function between A and B counts an alternating sum of the number of non-degenerate paths of length k between A and B in the poset. So in fact, it follows that, well, this I won't explain why, but from this you can get weightings and co-weightings, and then the magnitude is just the sum of all the components of this matrix. And in fact, this is the topological Euler characteristic of what is called the classifying space of A, which is the geometric realization of the NURB of A. Okay, so if you don't know what's that, okay, just forget it. But that's why this was called the Euler characteristic of initially. Now, if you have a general category, this matrix zeta won't be invertible in general. Okay, but what you can compute is that you can compute the Moore-Penrose pseudo-inverse, which is like another matrix that satisfies these equations. Okay, so here I'm using like matrix multiplication. And it is a theorem that I proved with Stephen Shen, which is somewhere here, and that in parallel some other people proved in Turkey, is that whenever A has magnitude, you can compute the magnitude this way. But this expression makes sense for any category. You don't need to have a weighting or a co-weighting. So in fact, this extends the definition of magnitude to any finite category. And in fact, Akaya and Undu proved that this is an invariant under equivalence of categories. So let's say like a decent definition. And in fact, what I've been working on the last months, but I don't have still a result to present. And that is like a generalization of Hall's theorem for this pseudo inverse. And in fact, you have something like that, but the story is a bit more complicated. So this also has a combinatorial interpretation. And what is nice about this definition is also you can see very clearly why the magnitude satisfies certain properties. So the magnitude is multiplicative under products of categories. And basically because the zeta function of the product of two categories is the Kronecker product of the zeta functions, seen as matrices. And the Kronecker product of, so the pseudo inverse of the Kronecker product of two matrices is the Kronecker product of the pseudo inverses. So you get, from that, you get the multiplicativity property. And similarly, there is an additivity property because the zeta function of the disjoint union of two categories is a block diagonal matrix. And then when you compute the inverse, you have this sort of block diagonal inverse. And ultimately, when you consider a discrete category, so a discrete category is a category that has objects, and the only arrows are identities. So it's like arrows that go from an object to itself and don't do anything if you want, like an identity map. Then this magnitude is the cardinality of the set of objects. So this is why Leinster said that like the magnitude can be seen as a generalization of cardinality. So in particular gives you the cardinality for a discrete category, which is like the natural way of regarding a set as a category, as a discrete category, but also has these properties that are reminiscent of cardinality. Okay, so we can see this as a generalization of cardinality. There's a last thing that I'll say, but this is way more technical. It's like you can do all this story for something that's called enriched categories. So in the case of enriched categories, these sets live in a symmetric monoidal category that now you have heard of. And you have additionally a map that somehow assigns a number to every isomorphism class in this category V. And so that you can define the zeta function as the number associated to the object on AV. And you can invert this matrix, so you do the pseudo-inverse business, and then you can define the Euler characteristic pretty much as we did, like the sum of all the components of the pseudo-inverse. So of course, a first example is like an ordinary category is just enriched over sets, and this map is just the cardinality, and what you find is just the thing that I presented before. But you can also regard the metric space as an enriched category. Well, I won't enter into the details, but what you will find is what is called the magnitude of a metric space. So the Euler characteristic of the metric space is an invariant, an isometric invariant of metric spaces, and it's called the magnitude. Okay, and this magnitude knows a lot about the geometry of the metric space. Like knows, I don't know, if it's finite, it will know how many points there are, but it's also, if it's infinite, it will know the volume and the surface area and other things. So, yeah, well, I won't enter into details there. But now, the entropy. So the entropy, in fact, can be seen as a probabilistic generalization of cardinality. And this is clear from Boltzmann definition. Now, Boltzmann defined the entropy as the logarithm of the number of microstates. Or if you want, this is the formula for the entropy, and if you evaluate it in the uniform law, then you find the logarithm of the number of states. Moreover, like additivity of the entropy gives you in particular the multiplicativity of the cardinalities. So now the multiplicativity of the cardinality is implied by this more general additivity property of the entropy. So in fact, you can regard H as a probabilistic generalization of the cardinality, or of course the logarithm of the cardinality. Okay. So the problem is now to complete the square. You know, we have a probabilistic generalization of cardinality, which is the entropy, and a categorical generalization of cardinality, which is the magnitude, and we'll like to find something here. And of course, we wanted to coincide with Shannon entropy for discrete categories, because those are like sets. And we would like to give us the log of the magnitude when we take a particular choice of the arguments, which could be something like the uniform distribution. Okay, so that we recover the familiar properties. Well, this you'll see later. We can do that. So we take the entropy. So now I'm going to explain what is this categorical entropy. Okay, Now, the entropy is the entropy of a metric space. So sorry, of a measurable space. So you need, let's say, a finite set with a probability mass function. In this more general setting, we'll have a finite category, a probability mass function on the objects, which is a finite set. But now there is this new ingredient, which is a function that goes from the product of A with itself and goes to the positive numbers, that assigns a positive number to every pair in the diagonal, and that is 0 whenever there is no arrows from B to B prime. So for example, the zeta function that we introduced before is a function like that. The Kronecker delta, so the function that assigns phi AA equals 1 and phi AB equals 0 whenever A different from B, that's also a function like that. And from a metric space, in fact, the corresponding function would be this. So you see like the objects of A as the points of the metric space, and this function phi or theta, I write it here, sorry, this phi should be theta. M prime is exponential of minus the distance between M and M prime. Or another example that I'll consider later is like you consider this theta AB as a probability of transition between B and A. Okay, so these transitions, the allowed transitions happen along the arrows of the opposite category. So when you have two triples, so I call this like categorical probabilistic triples. And when you have two triples, you can do certain operations. So you can multiply them. This could be something like the product of two measure spaces. And you can do this convex combination, okay, where with probability lambda you are taking points from A, and with probability 1 minus lambda you are taking points from B, but otherwise you use the loss P or Q that you started with. Now, so this A has a low P and B also has a low Q, and here you're doing a convex combination of those two. And because A and B are disjoint in this construction, because the sum takes the disjoint union, the transitions are disjoint too. So how many? Oh my God. Sorry? Seven. Okay, yeah, not too bad. Okay, so we can do this operation, okay? Product and convex combination. And also there is a notion of convergence. So you can say a triple converges to a given triple if the categories coincide eventually, okay, for all the k's that are greater than certain k0, and the functions converge pointwise. Okay, which of course makes sense because AK will be equal to K. Okay, so this is just the preliminary. No, we're trying to see this is the kind of object on which we want to define an entropy. Now the definition of the entropy is this. So to a triple, we're going to associate this number, which is minus the sum of PA logarithm of this sum. Okay, so you get phi AB PB. So remember, so one example would be this, taking this to be a probability of transition from B to A. So this could be something like the probability of A after one transition has happened. Okay, so that's how you can think about this thing. And whenever the argument is whatever you like, but this is 0, we are going to consider that the whole term is 0. Okay, this is how this is defined. And this quantity appears already in a non-categorical context as a diversity measure. So it's okay, so I won't enter into the details here, but somehow this also work by Leinster and Cobbold on diversities, on measures of metric spaces, okay? So yeah, it's not a completely new functional form, but now what is new is that we're trying to see this as this categorical entropy rather than something that is associated with metric spaces. And the proposition, I mean, this is like gathering many propositions. Okay, now 5 minutes. Okay. Gathering many propositions in the text is that okay, this H has the following properties. If you consider H of a category with a certain probability, but you take the transition kernel, this function phi to be the Kronecker delta, then you'll recover the Shannon entropy. So in particular, this is telling you for discrete categories, for discrete categories, the only transition kerning allowed is delta. So for discrete categories, you'll have Shannon entropy. Then this entropy is additive for products. So if you take the entropy of a product of two triples is the sum of the entropies. And it has this sort of like chain rule for like the weighted sum. Okay, so the entropy of the weighted sum is lambda times the entropy of the first, 1 minus lambda times the entropy of the second, and the entropy of this. I mean, this is complicated notation for the entropy of lambda, the entropy of the little coefficient lambda. And moreover, this function h is sequentially continuous. Okay, so it has a lot of good properties, analogous to the properties of the entropy. And there is also this part, which if you have a triple, and you have that this function phi has a weighting and a co-weighting. Again, the weightings and co-weightings can be defined for any matrix, not necessarily the zeta function. So you suppose that phi has a weighting and co-weighting, a magnitude phi. Then if phi has a negative weighting, the normalized weighting is a probability distribution. And when you evaluate the entropy on this probability distribution, you recover the logarithm of the magnitude. Okay, so under this hypothesis of a negative weighting, the magnitude is always positive. So it makes sense to write logarithm of the magnitude. You could do this more generally, because I mean, in general, a matrix might have only sign weights. So of course, the most general statement is allowing the weighting to be signed and adding an absolute value here. But of course, then we don't have a probability distribution anymore. No? It's more like a sign probability distribution. So that's something that you can write down and it makes sense, but maybe the probabilistic interpretation is a bit more delicate. So in general, this is the remark. U is in general a sign probability if we just took any weighting. So good. So it seems that, okay, this is pretty much the function that I was looking for, but of course, it's not completely satisfactory because we would like to distinguish this function among all the possible functions that maybe have similar properties. So the last part of the talk is towards a characterization. So we'd like to say, okay, this is the only function that satisfies this property. So but maybe these properties are not enough. In fact, I'm going to conjecture that they are not enough. In order to do that, we were inspired by like what Leinster, also with John Baez and Tobias Fritz did about the algebraic characterization of the usual entropy. Okay, so that theorem comes in 2 slides, but first I will introduce this sort of general notation so that we don't have to do it twice. So I will introduce a category of probabilistic finite categories. Okay, so it's like the objects are these probabilistic triples that I introduced. But then you have arrows that are given by a functor. So I have no time now. 2 minutes. The arrows are given by a functor, and then the functor preserves the probability and the kernel in this sense. Okay, yeah, okay. I won't enter much into this function. This is just like marginalization of probabilities. This is telling me that the transition at the target level is a weighted sum of the transitions between the preimages. Okay, you want to consider the transition between B and B prime. You look at all the preimages of B and all the preimages of B prime, and you take a weighted sum of all the transitions in A between those preimages. Okay, so you have these formulas, and then there is lemmas 1 and 2 in the proceedings is that this is indeed well defined. This defines a category. The composition is what defines all that. And moreover, you have like a refined definition of also what it means for a morphism to converge. So it's similar than before. The categories are supposed to be eventually equal to the target thing, but also the morphism is supposed to be equal when n is big enough, and then all the other things converge pointwise. Okay, so it's like a dumb notion of convergence if you want, but it's like the simplest thing that one can think about. And so this is convergence, and then the theorem by, I don't know. The thing is like, now I see that it's a bit delicate, like to explain this, like in the time that I have. But basically, you can see finite probability spaces, just pairs of a set with a probability, as embedded in this larger category. So you get a notion of convergence for those two. And the theorem by Baez, Fritz, and Leinster was that, in fact, the entropy somehow gave you the unique convex, linear, and continuous functor from this category of finite probability spaces to the real numbers when you see the seen as a one-point category with the sum as the composition law. And what our proposition before shows is that indeed the functor that is given by the categorical entropy is also convex, linear, and continuous. So you're tempted to say, okay, maybe this is the only convex, linear, and continuous functor of this form. But well, we don't have a result of that kind. I think this is where things fail. And essentially they fail because in the case of a finite probability space, you can always write a finite probability space as a convex combination of one-point sets equipped with a trivial probability with certain coefficients. And you cannot do that for a category. So the categories somehow have more structure, which is given by the arrows, which means that you need a composition law, which is a bit more complicated than this convex linearity. Okay, I didn't even explain what the convex linearity was. But maybe for people that already knew this result, I'm hinting at something. Okay, well, I'll stop here because I'm already over time.